and Arvindan, who's here in the audience. I'm going to talk about certain aspects of tensor decomposition. We've seen tensors and their applications in several talks on the first day. I'll remind you about some of these things, so there'll be a little bit of repetition. So the origins of all this goes back to factor analysis, which is a very common way to analyze data. Let's say you arrange data about how much people like movies in a matrix, this is the famous Netflix matrix, or you look at students and test scores. And somehow there's a belief that this matrices like these, even though they're very large, have some kind of sparse or simple explanation. And one kind of simple explanation that's very popular is a low-rank decomposition. So if we could somehow decompose this matrix as a sum of rank 1 terms, then the belief is that there's some meaning in these rank 1 terms, so it's useful to try to look for such low-rank decompositions. One problem with this approach is that in general there could be many decompositions. You'd like to find a meaningful one. In some cases, a meaningful one is one that is non-negative. In some cases, a meaningful one is one that is sparse, and so on and so forth. Okay? So you have some data which somehow is a sum of, you believe is a sum of small number of rank 1 terms, and we'd like to find what these terms are because hopefully they give us some insight into what the data is about. Now, one problem with doing this with matrices is that unless we impose any further constraints on these factors, any suitable rotation of these vectors will also give you low rank decomposition. So, if I have AB transpose, I can insert rotation matrices Q inverse, and I also get an equivalent decomposition. Okay. So somehow in order for this to be meaningful, it should be the case that this decomposition is unique in some sense. Otherwise, there's no way in which I could distinguish. There's no way in which I know which one is the right one. Okay? So how do you know that you found the desired decomposition? It would be nice to have some kind of uniqueness property. So in statistics, people realized this a long time ago that when you work with matrices and low-rank decompositions, you have this so-called rotation problem. And so one way to get around this kind of rotation problem is to turn your attention to higher dimensions. So just as you talk about decomposition of two-dimensional arrays of numbers, matrices, you could also talk about decompositions of higher dimensional arrays of numbers, tensors. And such tensors arise in many situations. You could, for example, look at some variables and represent higher order correlations as a tensor, partial derivatives, etc., etc. So, for example, a three-dimensional tensor is just a collection of one-dimensional matrix slices. So each of these is just a matrix, right? So you have a collection of these matrices stacked together. Now, just as we talked about low-rank decompositions of matrices, we could also talk about low-rank decomposition of tensors. Right? In this case, a rank 1 tensor is just x tensor y tensor z. It's if x, y, and z are n-dimensional vectors, then this is a n by n by n array, where the I, j, kth entry is the product of the ith entry of x, the jth entry of y, and the kth entry of z. Right? And again, we could hope to take a tensor given to us and express it as a sum of a few rank 1 terms, just as we did with matrices. Okay. And the smallest such R is called the rank. Now, here's the amazing thing that was proved by Kruskal in 1977. He showed that under certain conditions, and I'll actually make this precise a little later, tensor decomposition is unique. So, any way of writing this tensor as a sum of R rank 1 terms must essentially be the same up to permutation and scaling. And this is different, fundamentally different from the matrix case, where we have this rotation problem. Kruskal, by the way, for the people in computer science, is the same Kruskal who did spanning tree. turns out he was actually a statistician. The spanning tree work was done very early in his career, but most of his career was as a statistician, and this was some of the work he did, which has now become a seminal result in the tensor literature. So I'll tell you what these rank conditions are in a little bit, but the take-home message is that somehow if you look for low-rank decompositions of these higher order objects, you have uniqueness, and you don't have this in the matrix space. Okay, so this result really paved the way for a lot of applications of tensor decompositions in a number of fields that I know very little about, but I do know that tensor analysis is used frequently in the psychometrics literature, the chemometrics literature, algebraic statistics, and so on and so forth. One way in which this uniqueness has been exploited is to show that if you have some kind of hidden variable model, and again we've seen a bunch of these in various talks on the first day. We'll see some more, or I'll remind you about some of these later in the talk. But right now at a very abstract level, you have some kind of hidden model that's producing data. Okay. We'd like to figure out what this model is. We'd like to figure out what the parameters of this model is. And one recipe in order to do this is you somehow compute a tensor. You observe the data. From the data, you produce a tensor such that there is a low-rank decomposition of this tensor. If you knew that low-rank decomposition, you would be able to recover the parameters of the underlying model. Okay? And now you appeal to uniqueness to say that, well, this low-rank decomposition is unique. So in fact, this implies that these models are identifiable.
So Moses, is the Pearson work on learning mixture of Gaussian or like that, that's like also in this framework?
Yeah, so he really introduced this method of moments, right? But he was looking at two moments, pairwise moments. Mm-hmm. But it's the same thing. So typically when you use tensors, you compute some kind of higher order moments, and then you say that, well, there is a correct decomposition of this tensor as a sum of a small number of terms, and this is basically unique. Right? So it is an instance of this method of moments that was initiated by Pearson. Okay. All right. So a result of Allman, Matthias, Rhodes uses exactly this framework and argues that because of uniqueness, various models are identifiable. Okay. And there are also algorithms due to Anima and her collaborators over several papers where they've used this framework to actually design algorithms that prove that certain learning problems are tractable in very different regimes from what we used to know before. For example, mixture of Gaussians and so on and so forth. So this gives us a new range of tractable problems in the learning literature. They're all based on this paradigm that you compute a certain tensor. This tensor encodes these parameters, and now you find a low-rank decomposition. So that's the general recipe in which these tensor decompositions have been used. Okay, let me tell you a little bit about this uniqueness result. What are the conditions, and so on and so forth. So let's say we have this tensor. It's a sum. It's a 3 tensor. It's a sum of r terms. We could write down each of these vectors a1, a1, a2, a3, stack them together as the column vectors of a matrix A, and similarly for B and similarly for C. Okay, so when I say T is A, B, C, what I mean is that T is the product of the column vectors of A, B, and C in this way. Okay? All right. So each of these A, B, C are n by r matrices.
Sorry, T is just stacking of the vector, right? It's not...
No. When I say this notation, I'm not really going to use this notation very much, but when I use this notation, I mean that this tensor is obtained from ABC in this way. Okay, that's what I mean. All right. So what Kruskal said is that under certain rank conditions, on these matrices A, B, and C, this decomposition is unique. Okay? So in order to describe what these rank conditions are, I need to introduce a certain notion. So before I say that, of course, this uniqueness is up to permutation and scaling. So there's nothing special about the first term, there's nothing special about the second term, and so on and so forth. I could obviously permute them. And of course, I can also individually multiply the A, B, and C by scalars so that the scalars multiply to 1. Okay. All right. So, so this uniqueness is defined in terms of a certain parameter that is called the Kruskal rank. What is the Kruskal rank? It's the following. Given a matrix A, look at the largest K for which every K subset of the columns of A is linearly independent. Okay. And the largest such K is called the Kruskal rank of the matrix. Okay. All right. So this is a stronger notion than rank, right? Rank just needs one subset, one large subset that's linearly independent. This says that every subset is linearly independent. And this is somewhat reminiscent of restricted isometry, though not quite. It has a flavor of restricted isometry. Okay, so now, having defined the Kruskal rank, the theorem that Kruskal proved is that if the rank is small enough, it satisfies this condition, 2r plus 2 is less than equal to the sum of the Kruskal ranks of A, B, and C, then the decomposition is unique. Okay? So, one case you should think about is if A, B, and C are full rank, they have rank as large as possible, n, right? The Kruskal rank cannot be larger than n, then the decomposition is unique up to rank up to roughly 3n over 2. And there are generalizations of these to higher order tensors as well. Roughly speaking, if you look at the statement for higher order tensors, you have the sum of the Kruskal ranks on the left hand side. On the right hand side, you have 2r plus some term which is linear in the rank of the tensor.
Just for context, most tensors have quadratic.
Yes, good point. So as Nadi points out, most tensors in fact have quadratic rank. And I'll actually refer to some results about that are sort of related to this.
By some counting or something, you can show that it's usually unique. Like if you take a random 3 tensor, the rank is usually unique, or is?
Good question. So two results, right? One is that typically tensors have rank which is quadratic, right? 3 tensors. And secondly, what can we say about uniqueness of typical tensors? Okay, so usually the notion of typical that's used is this generic notion. So you say that if your tensor is such that all of the values don't lie on any low-dimensional manifold, don't satisfy any algebraic condition, and so on and so forth, then what can you say about the rank of this tensor? It's known that under this generic condition, tensor decomposition for 3 tensors is unique up to something like n squared over 16. Okay?
So if you choose a random, not a random 3 tensor, but a random sum of n squared over 16 rank 1 tensor, then that will be the only decomposition?
Yes, that will be the only decomposition. Exactly.
This kind of rank isn't become, right? Computing this.
Yes, we don't know how to certify or compute or prove bounds on Kruskal rank. And, again, it's very reminiscent to restricted isometry.
It's a youth of a matrix, right?
Yes. So it's very similar, and we have the same difficulties that we have. Okay. Yeah.
Is it easy to see that it doesn't matter whether you look at A, B, or C? So the Kruskal rank will be the same.
No. I mean, the Kruskal rank of A, B, and C can be very different, right? Because there's no connection between, A, B, and C are arbitrary column vectors. The tensor is just the sum of the tensor products of the ith column of A, the ith column of B, and ith column of C. But a priori, there's no connection between A, B, and C. It could be the case that A and B have high Kruskal rank, and C happens to have very low Kruskal rank. In fact, we'll talk about such situations in a bit. Okay? Yeah.
So just a remark on the generic case.
Yes.
I think what's expected most of the time for generic is it's not unique, but if you just do generic minus 1, then it is expected to be unique, but not known.
I see. So the bound n squared over 16 is not it could actually potentially be much larger.
Well, up to
Up to
whatever,
n squared.
you know,
Yeah.
3 or 2, whatever it is.
Okay.
But that's just what's expected, not what's known.
And-
I just want to make sure that I can
But for
understand the
generic
statement.
not being unique, that's pretty much understood.
Generic up to certain rank R, it is like choosing R random rank 1 things and summing them up.
Right, somebody who doesn't like you can easily find one that's not unique
Yes,
of any given rank.
but if you choose like a random rank R thing, then up to 1 less than the maximum rank, it will likely be unique or believed.
That's
It's
the belief.
believed to be
Believed.
unique and known to be unique up to whatever. Giorgio should know the exact. I think it's.
Well, I think this belief is proved the product of the factor is bounded by 10 at power 5, so quite a lot.
If the product of the factor.
Is the product of, yes, of the sides of the
Oh, I see.
dimensional.
But he's doing n by n by n, so.
Yeah.
Yeah, pretty large. Oh, so
In this case, n cube, yeah.
I see. So for large enough, you actually can prove that there is unique up
They're
to.
small enough.
For small enough.
Oh, for small enough. Okay. All right. Good. I'm hoping to learn as much from the audience as I hope to convey to you in the talk.
So Moses, one thing, I mean, the Kruskal rank is also very closely related to error correcting codes, right?
Error correcting codes.
Of course, that's the
Yes.
condition that you want from the parity check matrix.
Mm-hmm.
If it's not reals, if it was finite field.
Yeah. Other questions, comments? All right. So this is Kruskal's condition, and as we've said, in the generic case, we expect this bound for uniqueness to be much higher, and we know that that's the case. All right. So let's take a step back and let's remind ourselves where we were using tensor decomposition. Remember this recipe that I said. We have some sort of hidden latent variable model. It's producing data. We have some way in which we can compute a tensor such that a low-rank decomposition of this tensor somehow encodes the parameters of the model. We compute this tensor from the data that we have, and then we appeal to uniqueness and say, we're done. Okay, this is identifiable. Now, let's not worry about algorithms for a second. Let's just talk about the identifiability aspect. One issue that you have when you try to apply tensor decompositions in this way is that you don't really have access to the real tensor, which is the real moment tensor or whatever it is that you were trying to compute, right? You only have approximation. You have an empirical approximation based on the data. So whatever tensor you're trying to decompose, you have an estimate of the tensor, but not the exact tensor. Okay. Now, Kruskal's result does not really apply in this case. So technically speaking, Kruskal's result just says, if you had the exact tensor, then in fact decomposition is unique. This theorem doesn't say anything about errors. Okay. Now, from the point of view of identifiability, this is fine. Basically, identifiability says that with access to potentially infinite number of samples, you can basically identify the parameters. Okay. But from the point of view of understanding how many samples you really need, is it polynomial, is it exponential? Unfortunately, this doesn't say anything. Okay. So, our first foray into tensor decompositions was motivated by trying to understand this issue. Is it possible to come up with a robust version of Kruskal's uniqueness theorem? By robust, I mean one that can handle errors. Okay, so that's what we did in a result with Aditya and Arvindan. We showed that we basically gave a robust analog of Kruskal's result, exactly the same result, where now we're not given the tensor exactly, we're given the tensor with up to some error. We can recover the factors A, B, and C up to some other error if the sum of the Kruskal ranks satisfy the rank condition. Okay. Now we need to change things a little bit. The input error and the output error are polynomially related. Now our notion of Kruskal rank has to be some sort of robust analog of Kruskal rank, right? For Kruskal rank, we require that every k columns are linearly independent. Now that's a very weak notion, right? They could just barely be linearly independent. That's not good enough. What we need is that every k columns, if you look at that matrix, that has condition number that's bounded by tau. So we need to be able to bound the condition number of every k columns.
What is the condition number?
The ratio between the highest and the smallest singular values, that's it.
So Moses, can you prove it like in a black box way from Kruskal by showing that if you have this robust condition number, then when you add the error, you still have the original version of Kruskal rank large, or is that not?
Sorry, if you this is a stronger condition, right?
Right. No. So I guess one theorem you could prove that maybe then would reduce it to Kruskal 77 is that if you have a kr tau large, then when you add error, the original kr is still large. Is that what you prove? Or?
No.
It's when the error goes to t, not to the...
Yeah, exactly.
Okay.
So no, that's not how we
The error
prove
would be
it.
high rank or something. Yes.
So I should make one more remark. You could examine Kruskal's proof and say, all right, how can you actually come up with a robust version of Kruskal's proof? And at least the most direct ways in which we thought about doing this, it seemed to us that you would need exponentially small error in order to make the calculation work. So in other words, what would happen is whatever input error you have, the output error would be larger by an exponential factor. And what this means... Sorry? Yeah, there is an inductive proof, and the error blows up in that process. And this would mean that in terms of sample complexity, you would need exponential number of samples in order to identify these things. Yeah.
So this Kruskal condition is fairly standard in algebraic geometry. It's that if you think of these points, these k points, they're in what's called general linear position. Mm-hmm. That is, say, no 3 lie on a line, no 4 lie on a 2 plane, etc., all the way up to k planes. So is your condition sort of saying that no 3 points are close to being on a line in some very precise way?
Yes, basically that's what it is, right? Yeah. That's basically what the condition is saying.
So Moses, there is always I didn't want to introduce it, especially the experts here, but what about border rank? That is always a major problem when you're dealing with. So do these things break from border rank?
If the rank and border rank are different, you never have unique decomposition for rank.
So in particular, this means that in this range, the border rank equals the rank.
If the hypotheses of the theorem are satisfied, yeah, that's an assurance.
But also, this robust Kruskal rank implies something for border rank as well.
I'm still a little confused in the statement. So,
Sorry. Yeah.
In theory, you cannot recover A, B, and C exactly because you have this error. So how do you compute the Kruskal rank sub tau of A since you don't have it?
No. So I said before, we don't have a method to certify Kruskal rank, right? And similarly, we don't have a method to certify Kruskal rank tau of A or to verify it, right? What we're saying is that if you had a tensor that you were trying to decompose, and if you knew by some other means that this guarantee holds, then this thing would work, right? So now what this means is that if you're trying to decompose, a mixture of Gaussians or some kind of hidden Markov model or something, it implies some condition that should hold on the parameters of your hidden Markov model. Okay? But we don't have any way to actually verify this condition holds. Yeah.
So your condition on this robust Kruskal rank is sort of not invariant under scaling, right? Under these linear factors that you could exchange between A, B, and C.
No, it is, right? What do you mean?
As in, given a matrix, if you scale a vector, it changes the condition number of the matrix that you generate.
True.
Right, so you could imagine that, okay, I will pick the best scalings amongst times each of the columns that gives you.
Yeah. Say you have the best search scaling.
You know
Or, sorry.
You know how to do this? How to juggle these constants between A, B, and C?
No. So what we're saying is that if we are given a tensor with ABC, where ABC satisfies this condition, we're not actually trying to find the best search scaling, then this holds, right? So, similarly to the fact that we don't really know how to even certify what the Kruskal rank is, we're not actually going to try to find the best scaling and so on. Okay.
You said condition number was a ratio, right?
No, but if you just scale one guy, then it changes, right?
Don't scale
What Sushant's question was the following, that we said when you look at tensor decomposition, you can multiply the AI, BI, CI by scalars so that they multiply, product is 1. So you could arbitrarily scale one guy and scale down the other fellows, but this could have a very bad effect on this robust Kruskal rank.
So this is like this restricted isomorphic properties. So how does it compare to the results that people do in that case? I mean, somehow there's extensions of nuclear norm, regularization, whatever, to the tensor case. Somehow, how does
this condition compare?
Yeah.
So I'm not sure I
So
know
you get
what
recovery conditions are based on things about, at least superficially.
So does it apply to tensors directly?
There's versions. There's more general versions of just. Yeah.
Okay, so I'm not sure I know. I'm not sure I know how what the conditions are when you look at those. Okay. All right. So I'm not going to tell you what the proof of this is. I'll actually focus on something else for most of the talk. But just some comments on what this means. As I said, because our blow up in error is polynomial, this means that with the polynomial number of samples, we can actually decompose tensors. And in general, they are the few results on tensor decompositions when A, B, C are not full rank. And this gives you something for that case as well. Okay. All right. One big drawback of all of this is that both Kruskal's result and our result are not constructive. Right? So we have a proof of uniqueness, but it doesn't actually give you an algorithm. There are algorithms known for certain cases, for the so-called full rank case, where 2 of A, B, and C have rank R. And actually we'll see this algorithm in a little bit. In general, finding tensor decompositions are known to be hard problems. In fact, Hastad showed in 1988 that finding tensor rank is hard. Hiller and Lim in 2008 showed that almost all tensor problems are hard. In fact, that's the title of their paper. Yeah.
Sorry, so tau and R have no relation to each other. In other words, R could be so large compared to tau that by the time you do the error perturbation, your Kruskal condition is completely gone. Is that possible?
No. So, in the dependence on error prime, the connection between error prime and error, there will be some dependence on tau.
But R could be arbitrarily large compared to tau. There's no restriction on how large R can be.
But then maybe you'll get a meaningless.
Yeah, it's not clear, right? If
you would get meaningless stuff, presumably,
because
right?
R prime would be
Because
so
you
big.
destroy Kruskal condition completely where it's very large.
Yeah. And you can drive, the point is you can drive this error down. As long as this is an empirical average from your data, you can drive the error down just by taking more samples. So that was the point. The point is that we can choose error to be sufficiently small such that even with this blow up, this new error is meaningful. It gives you some information.
In some sense, the way you think about it is that you're given R prime and tau, and then you compute how many samples you need. You compute R and you know how many samples you need.
Yes, exactly. You got to work backwards.
So, when you are these algorithms effective or?
No, they're not. Oh, sorry. Which ones? These?
Well, you said algorithms known only for full rank case. Are those effective algorithms, or they're just sort of?
The polynomial time algorithms. We'll see one of them.
They're polynomial.
They're polynomial time, yeah. And these are actually very old algorithms. The earliest one that we know is dates back to work of Harshman, who in turn was analyzing an algorithm to do generic. And
Old enough that there's no year next to it. So.
I forgot the year. I think it's close to it's either 60s or 70s.
Actually, an algorithm works only if R is smaller than n, I think, because you use eigenvectors. So
Yes. It works in the case when R is less than equal to n.
But that's implicit, right? Because two of them have to have full rank. They can only have rank up to n.
Yeah. Right. The rank can be at most n. When I say that the rank is R, then R can be at most n. Okay. In general, finding tensor decompositions is hard. And there's an open problem that actually has some money attached to it. Can we get an effective version of Kruskal's theorem? Can we get an algorithmic version of Kruskal's theorem? Okay.
It's your money? Or
1/4 of that money is mine, yeah. Okay, so let me turn now to the algorithmic aspect. I talked about just this uniqueness and identifiability and so on. Let me turn to the algorithms. So before we talk about algorithms, let's go back and review in what situations we encounter tensor decompositions for learning problems. So as I said before, there's an assumption that some kind of model is generating data. In fact, you have some model, maybe it's documents or whatever. You hypothesize that the data is actually produced by some kind of model, and then you try to learn the parameters of this model, right? Okay, so let me talk about two kinds of models. One is learning mixtures of Gaussians, which many of you must have seen before. If not, you've certainly been reminded on day one. You have R Gaussians. The means are mu1, mu2, mu_r. They have mixing weights w1 to wr, the sum up to 1. And data is generated the following way. You pick a Gaussian with probability wi. Having picked the ith Gaussian, you sample a point from this Gaussian. Can you repeat this process many times? That's your data. Given this ensemble of points, you'd like to reverse engineer and figure out what these means were and what these mixing weights were and so on and so forth. Another kind of model, also that we saw on day one, is a simple topic model for documents. Given a corpus, we like to attach some kind of meaning. We like to figure out what documents are about and so on and so forth. So the hypothesis is that every document is about a topic, and for now, pretend that every document is about a single topic. Each topic could be thought of as a probability distribution over words. So our model is the following. There are R probability vectors, PR. These correspond to the probability distributions for each of the topics. We have mixing weights W1 to WR. And the way in which a document is generated is the following. You pick a topic with probability proportional to WR, and then you pick words from that document with probability proportional to with probabilities given by the probability vector for that particular topic. Okay. You sample many such words, that's your document. Right? Of course, this is not really how documents are generated, but this is the hypothesis. And then you try to find the best setting of parameters that fits your model. Okay. All right, so what's the general recipe? The recipe is what I said before, right? We're going to take each of these problems and somehow reduce it to some kind of tensor decomposition problem. And how do we do that? We compute a certain tensor whose decomposition encodes these model parameters, and then we try to find this decomposition. Right? Okay. So for Gaussian mixtures, it turns out that, roughly speaking, we can estimate this particular tensor. So the sum over all the components, the mixing weight times the tensor product of the means. So mu_r, tensor mu_r, tensor mu_r. Okay, this takes some work. You've got to do some cancellations and so on, but basically you can estimate this tensor. Okay. So this is the n by n by n tensor.
Can we do this when you know they're not spherical?
So this is, under some conditions, right? You can actually handle the non-spherical. No. This is all spherical. Yes. This is all spherical. Right, so I'm hiding all these caveats under the rug.
So can you say again what this tensor is? I mean, I don't.
So suppose you have means mu1, mu2, mu r, right? This is the sum of the tensor products of the means, right? So you're looking at the rth mean tensored 3 times,
And
summed over all the components.
what does this represent, or how does this come up?
Well, for example, how do you produce it?
How did this arise?
Oh, how does it arise? Okay, so remember the Gaussian mixture model that we had before?
Yes.
You have data that's generated from this probability distribution. So, roughly speaking, for every point that you get, right, if you compute, say, x tensor x, sum it up, you expect to get a term like this.
So why do you stop at 3?
You can go higher. You can also go higher, right? Now, one problem with Gaussians is that you don't just get this term, you also get some other stuff, which I'm hiding here. Turns out, in some of those cases, you can remove these additional terms. One problem with going to higher order tensors with Gaussians in particular is, it's just hairier to deal with all these additional terms that you get. So you have to worry about these additional terms and so on.
So that doesn't outweigh the uniqueness getting better.
So, for example, in the topic model case, it's much easier to compute higher order tensors. There, we don't have this problem. And yes, we can go to higher order tensors. And in fact, as you'll see, eventually when I talk about our results, we're not going to talk about 3 tensors at all. We're going to talk about higher order tensors. So, the issue with going to higher order tensors is one of complexity. Obviously, the algorithms take longer. The sample complexity is higher, but you can typically deal with a much higher rank. So there are advantages and disadvantages. Okay. All right. So for Gaussian mixtures, roughly speaking, we can compute this tensor, right? And I said how we compute it. We compute it from the data. You got to do some corrections, but forget about that. Don't worry about it. Similarly, for the topic model case, you can estimate this tensor, where instead of the mu's, you have these probability vectors, tensor 3 times, let's say. And instead of 3 tensor, you can compute 4 tensor, 5 tensor, 6 tensor, whatever you want. Okay. And the goal is, given these tensors that you've estimated, you want to figure out what these mu's are. Yeah.
So for these particular models or any others where you use tensor methods, were identifiability conditions known without these Kruskal type tensor theorems, or is this like the first time we have good identifiability conditions for these models?
So Gaussian mixtures, for example, have been studied for a long time, and the kinds of results that we knew typically were based on the separation between the means. Okay, so one kind of result says that if you have k Gaussians and the means are separated enough, right? I have to tell you what enough means. Then, given data from this mixture of Gaussians, I can actually recover the means.
But there's no question. For identifiability, that's not a problem, right?
Yeah. For identifiability, that's not. For identifiability, well, you also need some separation with the means. Beyond that, the problem is not uniquely identified.
Given that right now the proof of Kruskal's theorem is not algorithmic, like identifiability is what we should be worrying about here, right? That's all that Kruskal's giving us.
No. So you're okay with infinite samples? Under infinite samples, under very, very generic conditions, it's identifiable.
Okay. We're actually moved away from identifiability. We want to try to produce algorithms now. So I'm going to try to talk about algorithms. Okay. But yes, so there were algorithms known for mixtures of Gaussians and so on in slightly different regimes. What's nice about these tensor methods is that they give you results, without any separation assumptions and so on and so forth, which we didn't know how to do before. Okay. All right. So, as I said before, one big problem with this entire framework is that we reduced a problem that we didn't know how to do, this learning problem, to this tensor problem, and presumably we'll reduce to a very hard problem, right? Because we don't know how to solve these tensor problems, and there are all these worst case hardness results. The key point, though, is that these hardness results are in the worst case. Right? These NP hardness results and so on say that if you want to solve tensor decomposition in general, there's no hope unless P equals NP. Okay. Now, if you think about the kinds of instances that arise for which we would like to solve these problems, you could you could say, well, are these really worst case instances? So, I said for Gaussian mixtures, you have a tensor like this. For topic models, you have a tensor like this. Nature is not really conspiring against you to give you inputs that make your algorithm look bad. So, presumably, we should be able to do something for typical instances. Of course, the question is, what do typical instances mean? What are they really? So, we'll take inspiration from smooth analysis that was introduced by Spielman and Teng. That should be 01. I'll explain to you what I mean by applying smooth analysis to tensor decompositions next. Okay, so we're going to move away from worst case instances and say that if our tensors came from a certain smooth model, can we hope to learn them? Can we produce decomposition algorithms for such tensors? Right? Okay. So here's our tensor. Let's say a 3 tensor. And just to remind ourselves, these are what typical instances look like. Now, instead of assuming that these components A, B, and C are worst case, remember A, B, and C are, for example, means of Gaussians or the probability vectors associated with various topics. One kind of assumption we could make is that these components A, B, C are random. Okay? And that's a very strong assumption, and hopefully, well, it should be possible to do something for that, but it wouldn't be very satisfying. What would be much nicer is if we had something that sort of interpolates between worst case and average case. Okay, so not completely random, but has some elements of worst case. And that's what smooth analysis allows us to do. So the assumption is the following. Imagine that your components A, B, C are produced in the following way. Right? So you take worst case vector, you take arbitrary sets of vectors, AIs, BIs, CIs, and now for each of them you add a little perturbation. Okay. And that is your input. Your input is the tensor product of these perturbed vectors. Okay. So the assumption is that somehow, the means of these Gaussians or these probability vectors associated with documents are not in some worst case configuration.
So, if you had a mixture of Gaussians, then I guess there's some samples you can do where the expected value of those samples is that tensor. But do the fluctuations around it look like this, or would they?
No. So the assumption is the following, right? You had a mixture of Gaussians. I'm going to assume that your mixture of Gaussians the means were not in a worst case configuration.
Yeah.
They were actually produced in the following way. There was some worst case that you had in mind, let's say, but then I jiggled them a little bit. I moved them a little bit. Those were your means. You produce your entire data according to these perturbed means. And that's what I have to work with. Okay?
Estimates of the already perturbed.
Yes. All your estimates are of these already perturbed means. Right? So these perturbations are not errors.
Right.
They're just some natural variability in these instances, which helps us prove that for typical instances produced from this distribution, we're not going to have all
Just a
these
much stronger
hardness.
result than, say, doing it for random vectors.
Yeah. So, right. One assumption would be assume that your inputs are completely random. This is a much more nuanced notion of randomness, right? It says that, somewhere, pretty much around every point in your space, there is a very dense set. Pretty much all the instances that you look in a little sphere around that point are tractable.
So I guess it differs. Does it differ from other types of smooth analysis in that in some other cases, if you're given a worst case input, you could choose to add a little bit of noise to it, perturb it. But here it's not obvious that you can do that, right?
Mostly in smooth analysis you cannot do it.
Yeah, so the way Spielman and Teng applied this to linear programming was that they said, well, imagine you have a linear programming problem.
Yeah.
But, how are the constraints produced? They're not so start with arbitrary constraints, and now perturb the coefficients a little bit.
Yeah.
That's your linear program. That's the one you'd like to solve. Yeah. And they analyze simplex for that particular thing.
Just as Spielman and Teng didn't give a strongly polynomial time algorithm for solving linear programs, so Moses is not giving an algorithm for the worst case thing.
Okay.
Wait, this version of the algorithm, is that identical with what you're saying? Or you could, I mean, it makes perfect sense to do what you just described from Semidefinite 10. You take the tensor, perturb it slightly, this is what you're trying, and you take that as your input.
No, we're not doing that, right?
But what's the status of this? You know?
Wait, so you have a tensor, you perturb it slightly. The issue is these kinds of perturbations are very different from those kinds of perturbations. The perturbations you're proposing are basically noise, right? And we can deal with these easily. In general, it's much easier to argue about these kinds of things. But the trouble is, fundamentally you're not changing what these A's, B's, and C's are. They're still the same. So, in that sense, we cannot handle what you're. No. If I could, then I would be able to decompose general tensors, right?
I don't know that this is not true. So, I mean, for me, the way I'm thinking about smooth analysis, simultaneously and so on, is that in the space of all possible inputs to get the problem, presumably there are no bad instances at all. We cannot rule out the possibility of a solvable polynomial. But if they exist, they're very isolated. They're a very discrete set, in the sense that anywhere, I'm almost repeating the words that you said before, if you move random to a small distance, with almost certainty you're landing in a good place where this and that algorithm, the one that they analyzed, works. So this is a very satisfying situation. So I wonder if, what is the story here? Do we know that this is true? Is it possibly true?
I would imagine this is not going to be true.
Not really.
So if this were true, if this were true for low-rank tensors, right? So if you have a low-rank tensor and you add a little bit of noise, and suddenly the problem becomes easier, then by our identifiability result, whatever decomposition you get of this noisy tensor would be close to the decomposition of the original tensor. Okay.
You're moving away from a low-dimensional thing.
Yeah. And maybe there's an algorithm for low-rank tensors, but these hardness results, by the way, typically apply to much higher rank like n squared. Yeah.
Sorry, a quick remark, a clarification, right? Smooth analysis cannot help solve worst-case problems. Linear programming, in the worst case, we perturb it, it becomes completely different. Same here, presumably.
Yes.
As you just said, if you have a low-rank tensor and I perturb it, it will become full-rank potentially. So it's a different problem.
Yeah.
But it's saying the different problem might be easier. That's all it's saying, right? That's all it can say, I suppose, smooth analysis.
Yeah. But also, the point I was trying to make is that this perturbation that we have is, you should assume that your model has this perturbation built into it, right? This is not something that the algorithm does.
No, algorithm could do it, but it won't help the algorithm in the worst case. There's nothing preventing the algorithm from doing the perturbation.
But you would never generate these kind of correlated perturbations that
So you're saying
produce.
the individual vectors are perturbed rather than the tensor. Is that the difference you're making?
Yeah, because it makes sense, right? What are these individual vectors? These individual vectors are really the model parameters, right? So you could assume that the model parameters are not in a worst case situation.
Right.
And that's basically what this assumption is saying.
So
They're arbitrary plus some little perturbation.
Mathematically, it's order n independent random variables,
Yes.
not order n cubed.
It's not, yeah.
N cubed would be much more powerful.
Yes, you're right.
So I must say I'm really impressed by how, in a friendly way, you're dealing with all these interruptions.
That's okay.
Since you're an hour,
Well, when I first came here, before I looked at the schedule, I thought it was a 45-minute talk. So
we're used to this very much, as you know. So I wonder, there is work by Lim, and I forgot who the co-author is, where one thing that is very suggestive when you think about this from the point of view, so I'm now talking more or less under my head as a bioinformatician. People really, when they were really interested in looking for a high-dimensional analog of SVD, which is so useful. And then they have a paper, Lim, I forget who the co-author, like that, exactly, Lim and the Silva, which shows, so I don't really remember the details, but essentially there is no such thing in high dimensionals. And I wonder if this,
There's no analog of SPD in higher dimensions.
everything that you could think breaks, and, you know, the notion of sets being not closed, and so you need bubble and everything. And I wonder if this gives this thought a new chance of resurrecting that.
I'm not familiar with that work. I don't know. It's an interesting thought. Okay. All right. In the interest of moving forward, all right. I should also mention that this smooth model that we came up with was also considered pretty much in parallel by another group of people: Anderson, Belkin, Goel, Rademacher, Voss. I'll say a little bit about their results. They considered a similar model. They applied it to learning Gaussians and so on. The nature of the results that we have are slightly different, and I'll elaborate on that later. Okay, so I mentioned that there are algorithms for tensor decomposition in certain cases. Okay, at a high level, we're going to fall back on these well-known algorithms. We don't produce a new algorithm. We're just going to fall back on this old algorithm. So I should tell you what this old algorithm does. Okay, so here's the algorithm. So you have this tensor, sum of rank 1 terms. What these algorithms basically say is that if 2 of A and B, 2 of these matrices A, B, C are full rank, then we can recover this tensor. Okay, and let me tell you how you can do this. Okay, so one comment in going forward. These kinds of algorithms, there's no hope to do them in the so-called overcomplete case. When the number of rank 1 terms that you have, the rank of the tensor is much larger than n, we cannot hope to do this. In fact, hard instances, the known NP hardness and so on, they do have high rank. It's precisely these overcomplete cases where all of our algorithms fail. Okay, so these are the cases that we would like to produce new algorithms for, and we don't know how to do that. Okay. All right. So let me tell you about this generics algorithm, which goes back several decades. The starting point of this is the following. So suppose I have 2 matrices that have a common diagonalization. Right? I have M1, which is X D1 Y transpose, and M2 is X D2 Y transpose. So both M1 and M2 are linear combinations of, Xi tensor Yi, but with different coefficients. Coefficients are given by these diagonal matrices D1 and D2. Okay. The claim is that if D1 and D2 are sufficiently different, and I'm not going to elaborate how different, then basically we can recover X and Y. How do we recover X and Y? For example, you compute M1, M2 inverse. From this you can recover X. And similarly, you can compute M2, M1 inverse. From that you can recover Y. And then you can pair up the X and Y. Okay. So a simple algorithm. What does this have to do with tensor decomposition? Well, if we look at the tensor, okay, let's look at the nth slice of the tensor. I'm slicing according to this mode, second mode. The nth slice of this term is basically AI outer product CI with some coefficient. The coefficient is given by the nth coefficient of the vector BI. Right? So the point is this. If you look at all of the slices of the tensor, they basically have a common diagonalization. Just the coefficients that multiply these terms are different, right? So presumably we can apply this previous algorithm to learn the A and the C vectors. Having learned the A and C vectors, we can learn B. Right? That's the basic idea. So you could almost run this just by looking at 2 slices. That doesn't quite work. What you actually do is you take 2 random combinations of the slices. These 2 random combinations are matrices that have a common diagonalization. You learn the vectors A and C from that, and then from that you recover B. Okay, so that's the algorithm. So in fact, this algorithm has been rediscovered many times. Basically algorithms with a similar approach have been used over the years in similar applications. in work that appeared slightly before ours, Goel, Vempala, and Xiao actually analyzed this algorithm and showed that this is also robust to noise. So this is a good algorithm to use. Okay, so we're going to fall back on this algorithm, all right? But I said there's a problem here, right? Remember, I'd like to produce algorithms that work for very high rank. So when the number of Gaussians we have is very large, the number of topics we have is very large, and so on and so forth. This is a fundamental limitation. This is never going to recover more than n terms. Okay? So how could we possibly apply this algorithm when we have high rank?
Well, that's another related question to that,
Yeah.
which is that there's other work that was presented in this workshop which suggested that this algorithm is not robust to noise. And that's why you would resort to something like a tensor power method. Is there a reason why? I mean, I don't necessarily believe that. I'm just wondering, is there a reason why you prefer this one? Is it as a matter of convenience over a power method, or is
So you need different kinds of assumptions when you look at the tensor power method to work. So for example, you need some kind of incoherence assumptions and so on. So, one drawback of using our methods is that they're not going to give you practical algorithms. Right? So this is more sort of a complexity theoretic view at the problem.
why?
As you'll see, we're going to need, higher order tensors, and the sample complexity is going to depend. It's going to be polynomial and so on and so forth, but the dependence on the order of the tensor will be pretty bad. So in that sense, it's not, those algorithms are probably much more practical. Those are the things that you might want to use in practice. But they typically need stronger assumptions on the data. And we're going to we're making much weaker assumptions on the data. This kind of smooth assumption says very little about incoherence. So that's what. So, you lose some, you make stronger assumptions, and you get much better, much practical algorithms.
Is it clear that the algorithm is so different? I mean, because now you have this common diagonalization, and you try to compute maybe, try to do it with some kind of power method. I mean, wouldn't...
Well, I didn't say anything about these vectors AIs and CIs, right? And they could be roughly in the same direction, and then power method things won't work very well.
I guess I'm wondering just if you implement the algorithm, like you would, when you have to, diagonalize this. You have to invert the other guy before. I mean,
Yeah. Maybe you should ask the authors of stuff. Anima and Majid were around and wrong. Okay. All right, let me get back and try to finish on time. A little bit over time. Okay, so here's the basic idea. I said, look, we have a large number of terms, but we don't have enough dimensions. We have dimension n. So what we're going to do is, instead of our n-dimensional vectors, we're going to produce higher dimensional vectors and hope and pray that these vectors are in fact linearly independent. Well, we show that these vectors are linearly independent. Okay, how do we do this? Instead of computing a 3 tensor, how about computing a 6 tensor? Remember this data came from some model and we computed moments and so on. Instead of computing third moments, how about 6th moments? Okay, we can compute as high moments as we want. So let's look at 6th moments. Now what we're going to do is we're going to combine these two modes and these two modes, and think of this as an n square dimensional vector, this as an n square dimensional vector, and this as an n square dimensional vector. Okay. So this is a 3 tensor consisting of n square dimensional vectors. And now we have some hope that perhaps these vectors are full rank. Okay? The original vectors AIs were not necessarily full rank. But once we take tensor product in this way, we could hope that the resulting vectors are in fact full rank. Okay? So that's what we're going to do. We're going to compute a high order tensor. We're going to do this flattening. We're going to collapse several modes into one. And now we're going to apply the 3 tensor algorithm, provided we can guarantee that we have the rank condition that we need. Okay? So that's the question. If I have these arbitrary vectors AIs with these little Gaussian perturbations, can I prove, or is it true that these vectors are linearly independent? Okay. So if you don't remember anything else of this talk, this is a nice geometric nugget that I'd like you to take back. In fact, as you might suspect, the answer is yes. A proof of this fact is fairly messy. I'd like to think that there might be a much simpler, more elegant proof. It'd be very nice to prove this in a much simpler way. Okay, so let me tell you how our proof works roughly. So, some of the problems are trying to prove a result like this. These vectors have an inherent block structure, right? In terms of the perturbation that you have, perturbation is actually very correlated. As Ravi pointed out, there is, you have an n-dimensional Gaussian that's added to each of these, and you produce an n-square dimensional vector. So you have you don't have as much randomness as you would like. And what we prove informally is that given any sets of vectors, the A's and the B's, if you apply this perturbation, let's say the number of vectors is less than n squared over 4, with probably 1 minus exponential in minus square root n, let's say, this perturbation is good. Okay, these vectors are linearly independent, also the condition number is good, and so on and so forth. Okay. All right, this also applies to higher order products, but for this talk we'll just talk about products of two vectors. Yeah.
So a very simple question. So what are the n squared vectors that we'll show that have good condition number? AI times BI, and not AI tensor AI. You're not doing them as
AI times BI, yeah. But you can also apply it to, if you remember, our tensor was mu I, tensor mu I, tensor mu I. So it's the same vector mu I. We do some partitioning coordinates to pretend that these are different vectors, AI and BI. Okay. How much time do I have actually, since I'm
There were lots of questions. What do you say?
Running
How
every
long do
time
you wanna go,
5
man?
minutes.
Sorry?
How long do you want to go? That's an
I don't know, as long as you're willing to sit.
I think you're running 5 minutes.
Okay, all right. I'll 5 minutes. Okay, so let me try to give you a very, very brief overview of how this proof works. Okay, so as I said, it's a problem in proving a result like this is that our perturbations are very correlated, and the main technical contribution, I said, the one technical nugget I'd like to take back is this proof that these product of perturbed vectors in fact behave like random vectors, okay, in n square dimensions. Okay. In what sense? So here's the strategy. What we're going to try to prove is that every such product, perturbed product, has large projection onto the space that's orthogonal to the span of the rest. Okay. If we can prove this, we're done, basically. This is what we need to prove. This will imply a bound in the condition number and so on and so forth. So each of these vectors has large projection on the space orthogonal to the span of the rest. Problem is, the space of these remaining guys is also some kind of random space. It was produced by this perturbation and so on. We don't really have a good handle on what the space is. Okay? But instead of trying to say that it has a large projection onto that space, we know that this space is 3n squared over 4 dimensional, right? The space orthogonal is 3n squared over 4 dimensional. We'll say that this has large projection onto any 3n squared over 4 dimensions.
It's even less than that, so you're saying that.
Yeah. So we'll say that this has large projection onto any 3n squared over 4 dimensional. In particular, it must have large projection onto that particular space. All right. So now the proof of this involves a certain construction. I'm not going to be able to tell you very many details of the construction. I should say one thing. If you use results on anti-concentration of polynomials, you can get such a result, which will succeed with probably 1 minus 1 over polynomial. Okay, so the failure probability will be 1 over polynomial. One of our challenges was we were trying to get error probability which was somehow exponential. Okay. And at least it seems to us that shooting for this kind of exponential error probability seems to need much more delicate proofs. I said this would be a very nice result to prove. If there was a simple proof of this, we'd be very interested. Okay. Roughly speaking, we show the following. So in any 3n square over 4 dimensional space, there are some root n vectors, m1, m2, m root n. Now remember that this 3n square over 4 dimensional space is a space of n by n matrices. So viewed as a n by n matrix, these m1, m2, m root n have a special block structure. Okay? And the rough property is that, if you look at the ith column, it has enough projection orthogonal to the remaining columns. I'm not really saying this very well. I'm not really being very precise. But this is the kind of structure that we're looking for. We're looking for special vectors, m1, m2, m root n, in any 3n square over 4 dimensional, which have some nice orthogonality properties. And we show that we can actually do this, and this is the crux of the construction. I'll be happy to say more if you guys would like to hear more. All right. So a similar result holds for higher dimensions. You have to be a little more careful when you're dealing with not 2 tensors but higher tensors. So okay, let me tell you what the main result is. The main result basically says for higher order tensors, we can, in the sense of smooth analysis, we can compute decompositions for rank that goes up to n to the d minus 1 over 2. Okay, that's what we get out of this. Forget about the technical statement. There's some dependence on, if you look at d tensors, what's the exponential as a function of d and so on and so forth, but let's ignore that.
Maybe you should mention that. Most likely n to the d over 2 looks like an algorithmic upper bound, right?
Yes.
Although I don't know if there are any formal results showing something like that.
I guess here I was talking about what is the... Right, you could talk about the rank, how high a rank you can hope to get. And this, I presume, n to the d over 2 seems to be a limitation.
D over 2 seems like an algorithmic upper bound, but I don't know if there is any kind of result.
That says it. Yeah, I'm not sure. Okay. Let me finish. So this also applies to all these Bixter models and so on, provides results for those. I'm not going to tell you what the precise results are. Let me just contrast with this other paper that I mentioned by Anderson et al. So they get very similar results to what we get. As I said, we get exponential failure probability. This is the kind of failure probability that we get. They get polynomial error failure probability. Their sample complexity is polynomial in n and 1 over rho. Our sample complexity is also polynomial. The one key point is that the exponent of this polynomial in our case is exponential in d, and the exponent of the polynomial in their case is polynomial in d, something like d squared. So the problems are a little bit different. Somehow shooting for really small error probability seems to make at least our proofs much more complicated. Okay, let me stop with some open problems. It would be very nice to get robust uniqueness for ranks which are bigger than n, asymptotically bigger than n. And some members of the audience have shown that decompositions are typically unique up to n squared over 16. We discussed this very early in the talk. Can we actually get robust analogs of these results? We don't know. Some of these methods come from algebraic geometry, and at least we don't have a good way to understand whether or not you can produce robust analogs of those. In general, trying to decompose beyond rank n is a big challenge just for 3 tensors. Can we decompose under Kruskal's condition? Can we prove hardness in this regime? We don't really know. And some results of Anima, Rong, and Majid show that decomposition is possible in some cases. You can do this for ranks which are constant times n, but they need some sort of incoherence assumptions on their tensor. Finally, there's a dependence on error. I mean, the kinds of error that we can tolerate in these methods is really tiny. It's inverse polynomial in n. And one question is, do these methods completely fail if the error is constant? And there's some hope that we might be able to do something in those regimes. Results of Boaz, David, and John show that certain kinds of tensor decomposition problems, when attacked with this tool of sum of squares relaxations, do yield even under constant error. So that would be that's a promising direction. Okay, thank you for your patience.
Any more questions? A short question. I understand that your technique for even numbers, so for example for 6 you regroup 2, 2, 2, but assume you have a 5.
So actually, we don't need 6. I just put it there to be symmetric. What I said will work with 5, right? You only need 2 of the modes to have full rank.
I see.
And for the other one, you just need Kruskal rank 2. So in fact, we do it for odd numbers, in fact. I mean, the 6 was just for convenience, so I didn't have to confuse you by saying that we combine 2 modes and 2 modes and leave one in it.